So welcome to the third talk of this session. As before, please mute it during the talk and you may unmute yourself to ask questions. So we are very happy to have Matthew Dodelson from Kavli IPMU, who will talk about Chern-Simons invariants from ensemble averages.
Okay, well, thank you for the introduction. So this is based on work with collaborators from IPMU, namely Ashwin Kumar, Kidami, Lidam, and Yamazaki. And it's based on a paper we released last month. Okay, so here's the outline of the talk. I'll start by motivating the talk by introducing the concept of holography with boundary ensembles. So ensembles of CFT on the boundary. And then I'll introduce the model that I'll consider here, which is a free boson CFT associated to an integral lattice. In the next section, I'll consider the ensemble average of this model, and I'll show how this is related to the Siegel-Weil theorem. Then I'll turn to the bulk, and I'll show how the bulk Chern-Simons theory matches the ensemble average in the previous part. I have to treat the positive definite case separately, and so I'll do that in section 5. After that, I'll move on to spin CFTs, fermionic CFTs, and I'll show how this is related to spin Chern-Simons theory. And finally, I'll conclude by speculating on a possible duality before averaging and showing how this is related to introducing the Maxwell term in the bulk Chern-Simons theory. And then I'll conclude with some future directions. Okay, so let's start with the motivation. So the conventional statement of holographic duality that most of us are familiar with is that a CFT is dual to a bulk gravitational theory in anti-de Sitter space. So that means that the partition function of the bulk with a boundary source turned on is equal to the boundary partition function with source J. So that's the standard picture. However, recently it has been suggested that sometimes instead of computing the partition function for a fixed CFT, sometimes we need to replace that quantity by the average over a suitable ensemble denoted by brackets here. So the simplest example, due to Saad et al. And Stanford and Witten, is the duality between JT gravity and a matrix ensemble. So in JT gravity, we can compute the partition function with some circles on the asymptotic boundary. Beta 1 through beta n are their lengths. And then this is equal to the average correlation function of traced e to the minus beta h in a matrix ensemble. So that's an example in a two-dimensional bulk gravity theory. In the context of three-dimensional gravity, the situation is not quite as clear, but there's this indirect argument due to Kotler and Jensen that possibly there's an ensemble average involved there too. So in this calculation, they compute the path integral with two torus boundaries. And these two boundaries are connected in the bulk by a Euclidean wormhole solution. So the path integral on this Euclidean wormhole solution should equal something like a connected correlation function of two partition functions on the boundary. So if there is no statistical ensemble, then the partition function would simply factorize. And so since this thing is non-zero, this indirectly suggests some sort of statistical ensemble also in the three-dimensional case. A much simpler toy model than 3D gravity itself was discussed by Maloney and Witten and Afghani Jedi et al. In this case, instead of Einstein gravity in the bulk, they consider Chern-Simons theory with the gauge group U1 to the 2p. And the boundary ensemble that's dual to this Chern-Simons theory is the Noreen moduli space of a p compact scalar field. In this case, the average partition function can be computed using a special case of the Siegel-Wilde theorem. This theorem relates average theta functions to Eisenstein series. So namely, we average the theta function over the moduli space MP, and this is equal to the Eisenstein series on the right-hand side. Now, the right-hand side turns out to be the Chern-Simons partition function summed over all geometries with the torus boundary. So this is a kind of holographic duality between the left-hand side, which is an ensemble of CFTs, and the right-hand side, which is Chern-Simons theory. So that was the case considered up until now. In this talk, I want to consider a more general ensemble average. And it turns out that this will be related to a more general version of the Siegel-Wilde theorem. So instead of considering compact bosons on the boundary, we'll look at a wider class of CFTs defined by integral lattices. And we'll see that the average CFT partition function for these models is reproduced by the partition function of Chern-Simons theory on lens spaces. Okay, so now let's construct the models that I want to consider. So I'm interested in CFTs, and they have P left moving and Q right moving bosons. And so these are the vertex operators for that theory. So they depend on K left and K right, and they're the form e to the I K dot X. So to construct the theory, to define the theory, we need to choose some subset of these vertex operators to include. So there's a few constraints. So first, the theory must be closed under the operator product. And so what that says is that the allowed values of K left and K right form a lattice, lambda. We also want the vertex operators to have integer spin. However, we could also consider the fermionic case where they have half integer spin. And in fact, I'll do that later in this talk. But for them to have integer spin, we need a K left squared minus K right squared to be twice an integer. So what this means is that we have an even quadratic form with signature P comma Q on lambda. And the quadratic form Q is given by K left squared minus K right squared. We also have another function on the lattice, which is the Hamiltonian. This is not quantized. It doesn't have to be an integer. And all it is the sum of K left squared and K right squared. So now let's discuss the possible moduli space of such lattices. Well, if we have a lattice with quadratic form Q, there are many ways of embedding this lattice into a flat space with signature P comma Q. If M is a matrix that satisfies M transpose Q, M equals Q, and Q is the Gram matrix for lambda, then we can rotate the lattice to get an equally good embedding of the lattice. However, M is a symmetry of the theory if it preserves H, so that's not really a different theory. And also, there's a discrete subgroup of matrices that just permutes the lattice points. So we have to divide out by those transformations, which don't actually change the theory. And so the full moduli space is O of O P comma Q divided by OP times OQ, and again divided by OPQ comma Z, which is the discrete subgroup of matrices that I mentioned earlier. So this is the full Noreen moduli space, and it has dimension P comma Q, or sorry, it has dimension P times Q. So the simplest example would be a free boson on a circle. And in this case, the lattice is given by these values. So N and W are the momentum and the winding respectively. And P left and P right depend on a real number R, which is the radius of the circle. But this quadratic form P left squared minus P right squared is independent of the radius. And so this radius R parameterizes the moduli space of the theory. More generally, we could consider a higher dimensional toroidal theory. And then the moduli space is parameterized by the internal metric G and the B field B, and also possibly a gauge field A for a heterotic theory. Okay, so that defines the theory. And now we can easily compute the partition function on the torus. So this it depends on both Q, the quadratic form, and also the point in the moduli space M. And this is the value of the partition function. It's a sum over the lattice of e to the I pi p left squared times tau minus I pi p right squared times tau bar. And this is called the Siegel-Noreen theta function. So in general, the partition function is not modular invariant, but in general, it transforms in a covariant way under modular transformations. So to derive these modular transformations, I first need to define some more theta functions, which are the images of the original theta function under the modular group. So these are obtained by just shifting L by H, where H is valued in the discriminant group, namely the dual lattice modulatus. And the dual lattice is all X such that Q of X with L is an integer for all L in the lattice. So this is a vector of theta functions depending on H. Okay, so once I define those theta functions, I can define the respective partition functions. And the action of the modular group on the partition functions takes this form. So the T transformation, tau goes to tau plus 1, just multiplies the partition function by a phase. It depends on the Q of H, and also this the second phase, which depends on P minus Q, the signature of the lattice. Okay, so then there's also the S transformation, and that acts as a Fourier transform, a discrete Fourier transform. So it's a sum over the dual lattice modulatus. So the simplest example would be a self-dual lattice, so that lambda star equals lambda. In this case, the determinant of Q equals 1. So for example, the case of toroidal compactification with P equals Q, so signature 0, is an example of a self-dual lattice. So in this case, we see that this sum is just, it disappears because the dual lattice is trivial. And the theory is modular invariant when P minus Q equals 24 times an integer n. So I just want to point out also that the representation of the modular group is actually independent of the point in moduli space. So in other words, these transformations don't depend on the point M here. So what this means is that if there's a holographic duality after ensemble averaging, we should have some bulk interpretation of these above modular transformations. And indeed, we'll see that this is the case in Chern-Simons theory. Okay, so that was the construction of the boundary theories. And now I want to discuss their ensemble average. Okay, so we have the partition functions, and we also have a unique Haar measure, dm, on the moduli space. So I'll define the ensemble average to simply be an integral over the moduli space with measure dm, normalized by the volume of the moduli space. So this integral is computed by Siegel. If we demand p plus q is greater than 4 for convergence, then it takes the form, the average of theta is a Kronecker delta for h in the lattice, plus a sum over terms that diverge at rational numbers in the tau plane. So here, the coefficient of each of these terms is a quadratic Gauss sum, and it takes this form. So it's a sum over lambda mod c lambda, and there's a phase out in front. So to take the simplest example, for toroidal compactification with p equals q, we have gamma is equal to 1. So in this case, the average of the theta function just becomes the ordinary non-holomorphic Eisenstein series with weight p over 2. But more generally, we can think of this average theta function as some kind of generalized Eisenstein series EQ. So now it depends on the quadratic form Q. Okay, so Siegel gave a proof of the Siegel-Weil theorem by simply doing this integral above, but we can give a simple argument for this, the Siegel-Weil theorem without doing any integrals. So let's do that now. So the theta functions are not modular invariant, as I said before, but it turns out that they're invariant under a subgroup of the modular group. So this is given by the congruence subgroup gamma of n. So this is defined by A and D are 1 mod n, and B and C are 0 mod n. And of course, A times D minus B times C is equal to 1. So here I've defined n to be the smallest integer such that n times q inverse is an even quadratic form. So n is called the level of the quadratic form q. So since theta is invariant under gamma of n, that means that it's a modular form on the quotient of the upper half plane by gamma of n. So now this quotient has cusps at the images of tau equals I infinity under the modular group divided by gamma of n. So using the transformation law, it's possible to compute the behavior of the theta function near each of the cusps. So that's done by simply using the transformations on the previous slide. And what you find is that it exactly matches the behavior of the Eisenstein series. The theta function is a quadratic Gauss sum divided by these singular terms at tau equals minus d over c. So that matches the behavior of the Eisenstein series. The next step is to show that they both satisfy the same differential equation. And that's given by the Laplacian plus some number depending on p and q, acting on some power of tau 2 times f is equal to 0. So here I've defined a Laplacian on weight k forms, and it's given by this operator. So for k equals 0, this is the ordinary Laplacian. For non-zero k, this acts on weight k forms. And suppose that we have a normalizable eigenfunction f sub lambda, and it has eigenvalue of lambda. Well, we can bound this eigenvalue lambda using integration by parts. So the left-hand side here can be integrated to get the right-hand side, which is manifestly positive. And so as long as this integral converges, which it does for a normalizable eigenfunction, the eigenvalue is bounded from below. So what this means is that lambda is greater than k times 1 minus k over 2 over 2. Okay, so that's the two pieces that we need. So using this equation above, we see that the difference between EQ and the average theta function has eigenvalue less than lambda min. So it must vanish. It's normalizable because E and theta both agree at the cusps. So what this means is that E is indeed equal to the average of theta. So I should mention that for Q equals 0, which would be a positive definite lattice, the eigenvalue lambda is actually equal to lambda min. So this argument does not go through. And I'll treat that case in a bit. Okay, so that describes the boundary theory and also the boundary ensemble average. And now we want to match to the bulk Chern-Simons theory. Okay, so we've seen that the average partition function is equal to the Eisenstein series divided by the eta functions. And we would like to find the bulk interpretation of this partition function. So first we can match the symmetries. Sorry. On the boundary, we have a U1 to the P plus Q symmetry. That's simply given by the currents dx. And so the bulk should have a U1 to the P plus Q gauge symmetry. Okay, so that's the first piece of data. The other piece of data that we need is this integral quadratic form Q. In a Chern-Simons theory, the level matrix is quantized. And so a natural guess is that the bulk theory is a U1 to the P plus Q Chern-Simons theory, and it has the action whose level matrix is equal to Q. So here, the level matrix is the coefficient of the kinetic term in the action. So this is our guess for the candidate dual theory. We also had this parameter h up here in the average partition function, and in Chern-Simons theory, it will turn out that h will label the states of the Chern-Simons theory, and this will correspond to a Wilson line wrapping a non-contractible cycle in the bulk. Okay, so that's the theory, and now we want to match the partition function. So we need to sum over the geometries that asymptotically approach the torus at infinity. The relevant solutions are very well known, and I'll call them MCD. They're all quotients of ADS3 by a discrete subgroup of isometries, and they're labeled by an element of PSL2Z. So a couple of examples. M01 is simply thermal ADS space, and M1, 0 is DBTZ black hole. But in general, we have a geometry MCD for any element of PSL2Z. So now let's compute the partition function for thermal ADS. So this is simple. It's simply given by the U1 vacuum character for P left movers and Q right movers. And it's known that that's 1 over eta to the P times 1 over eta bar to the Q. Okay, so now to compute the contribution from MCD, we just have to apply a modular transformation, G, to this partition function. So the states on the Hilbert space on the torus are obtained by inserting a Wilson line with charge H valued in the discriminant group along the non-contractible cycle in the bulk. So to obtain the contribution from MCD, we have to make a modular transformation on the contribution from Z from M01. And so it's just given by the matrix element of this modular transformation in between the vacuum and the state H, divided by the transformed eta function. Okay, and then finally, we just sum over all group elements G. Although actually there's an ambiguity in associating G to MCD, and this ambiguity is given by gamma infinity. This is a subgroup isomorphic to Z, which is generated by the matrix T. So summing over the quotient of SL2Z by gamma infinity gives this form of the partition function. So again, we have these matrix elements in the numerator. So what's the interpretation of these matrix elements? So the numerator can be obtained as the partition function on an enclosed geometry, obtained by gluing two solid tori after acting by the element of the mapping class group on the boundary. So this closed geometry is called a length space, and it's a ZC quotient of the 3-sphere, Z1 squared plus Z2 squared equals 1 by a transformation given below. So here D and C are relatively prime because they correspond to an element of PSL2Z. And so one can show that this geometry is actually smooth. It's not an orbifold. And this is called the length space. So the partition function on a length space was computed by Jeffrey, and it takes this form. So indeed, it's equal to the quadratic Gauss sum from before, up to this phase. So the phase depends on the signature P minus Q, and also on this function, the Rademacher phi function. So this is a function on PSL2Z, and the transformation, the partition function depends on this additional function. So at first, it looks like there's an anomaly under gamma infinity, because it's known that the Rademacher phi function is not invariant under gamma infinity. And in fact, this corresponds to the framing anomaly in ordinary Chern-Simons theory. But in fact, this transformation under gamma infinity actually cancels the transformation of the eta functions. So I'll recall above, we have eta of G times tau, and the transformation of the eta functions under SL2Z also involves this phi function, this Rademacher function phi. And so finally, we're left with this final answer. And indeed, this is equal to the Eisenstein series divided by eta functions. So again, this is equal to the ensemble average of the original boundary theory. So I should mention that here we've considered the fluctuations only around the vacuum, A equals 0. But in a U Chern-Simons theory, we have to form a gauge invariant state. And so what this means is that we should actually sum over the large gauge transformations. This does not seem to give the right answer in our case, because summing over the large gauge transformations would introduce extra terms here. So it seems that the non-perturbative definition of the theory needs to be better understood, and that this theory so far only describes the fluctuations around the vacuum A equals 0. Okay, so that's the main part of my talk. But now let me discuss the positive definite case, which, as above, I explained was not covered by our proof. So our argument for the Siegel-Wiley theorem actually fails for Q equals 0. And in fact, we did not find a way to prove the Siegel-Wiley theorem in the positive definite case without actually doing the sum. So to discuss this case, we need some definitions. We say that Q and Q prime are equivalent in a field F if there existed some matrix G in GLP plus Q with coefficients in F, such that Q prime is equal to G transpose Q times G. The second definition is that Q and Q prime are said to be in the same class if they're equivalent in the integers. And finally, Q and Q prime are in the same genus if they're equivalent in R and in ZP for all primes P. Okay, so that's 3 definitions that we need. And it turns out that the theta function only depends on the class of Q. So to define the ensemble average in this case, we consider the average over a given genus. So that I'll denote by double brackets here in this formula. So the average over the genus is given by the sum over all the classes in the given genus of the theta function divided by the order of the automorphism group of the form of the quadratic form Q. So here H of Q is the class number. It's the number of classes in the genus under consideration. So the Siegel-Wiley theorem in this case says that the ensemble average of theta is again equal to the Eisenstein series EQ. So this idea of the genus is actually unique to the positive definite case, because for indefinite forms, it turns out that there's only one class in a given genus. So for example, when P equals 24, there's some, it turns out that there are 24 different even self-dual lattices. And this ensemble average is an average over all of these lattices called the Niemeyer lattice. Okay, so that was the partition function, but actually there's another theorem in the positive definite case that lets us consider some more observables. So again, I need some definitions first. So I'll say that a polynomial P of L is said to be spherical if Qij times Di dj P equals 0. So this is a polynomial, it's a function of the lattice variables, L. So one can show that if P is spherical, then this polynomial of dx, which is the boundary operator, is a primary operator. So it's an eigenvalue of L naught, and it's annihilated by all the other L minus n's. So in this case, it's simple to show that the 1-point function on the torus of this primary operator P is equal to a sum over the lattice of P of L times e to the IQ of LT, tau. So this is a more general theta function, which I'll call theta QP. So then once we have this theta function, there's a theorem due to Waldsberger. And this is a statement about the ensemble average of such correlation functions. So I'm just translating his theorem into our CFT language. And what the theorem says is that the ensemble average of these correlation functions is equal to a certain function. So it's the Hecke operator acting on C. C is known as Cohen's function. And the polynomials here are Gegenbauer polynomials. So this can be derived by taking the theta function of degree 2 and reducing it to get a spherical theta function of just a function of tau. So in this case, we have the ensemble average of this spherical theta function, but we don't have a bulk interpretation in terms of Chern-Simons theory. So it would be interesting to understand the bulk interpretation in this case as well. Okay. Any questions so far? Okay. So up until now, I've been discussing bosonic CFTs, which means that Q is integral. Actually, sorry, it means that Q is even. So now I want to consider integral, not even quadratic forms Q, and I want to allow for odd lattices. So what this means in physical language is that the spin can be half integral, so that we have a fermiont on the boundary. So first we have to derive the boundary partition function for these fermionic theories. So to motivate the result, recall the partition function for a free fermion. So it now depends on the spin structure. So these integers epsilon I are equal to 0 or 1, and the theta function depends on the spin structure epsilon 1 and epsilon 2. There's a factor of -1 to the epsilon 2 times L squared, and also a shift in the sum by epsilon 1 over 2. So this factor -1 to the epsilon 2 times L squared is simply -1 to the fermion number. It weights particles by -1 if they're a fermion, and by 1 if they're a boson. And epsilon 1 simply labels the periodicity on the spatial circle, R or NS. Okay, so in our case, we have a simple generalization of this answer. So here, again, the sum is shifted by epsilon 1 times W over 2. So I'll explain W in a second. And again, there's a factor of -1 to the epsilon 2, but now we have this factor of the inner product of W and L. So here, W is called the Wu class, and it's defined by the formula that the inner product of W with L is equal to Q of L mod 2. So in other words, -1 to the W of L is equal to -1 to the fermion number. And one can solve for W in terms of Q. It turns out that the components of W are equal to the diagonal components of Q. And finally, we have this dependence on epsilon 1. And that follows because e to the I W dot X over 2 is the spin field. So this creates a branch cut in fermions. It makes them antiperiodic on the spatial circle. So this is analogous to the bosonized spin field e to the ix left over 2 in the free fermion case. So in that case, that's what gives the shift by epsilon 1 over 2. Okay, so now let's consider the ensemble average. So to compute this average, we need to use a trick. So the trick will relate the theta function for an odd lattice to the theta function for an even lattice. So first consider this, the trivial spin structure. So that means that we don't have the shift in the sum or the factor -1 to the f. And the trick is just to multiply p left squared by 2 and p right squared by 2 and divide tau and tau bar by 2. And so this theta function is equal to the theta function for 2 times q evaluated at tau over 2. Now 2 times q is an even quadratic form, and so we know the average of the theta function on the right hand side. We can just use the ordinary Siegel-Wilde theorem, and so it follows that the average theta function with trivial spin structure is equal to the Eisenstein series for the quadratic form 2q evaluated at tau over 2. And I'll define this to be the Eisenstein series with 0, 0 spin structure. And it's possible to simplify this expression. It looks like it did before, but now there's a congruence condition in the sum. Namely, C and D are still coprime, but now C times D has to be even. So that's an additional condition in the sum. Okay, so that was the trivial spin structure. And now we want to know the other spin structures. To do this, we need to know the action of the modular group on the theta functions. So I'll consider the self-dual case for simplicity. Then the T transformation acts by exchanging theta 0, 0 and theta 0, 1. And it just acts as a phase on theta 1, 0. And the S transformation acts by exchanging theta 0, 1 and theta 1, 0. And there's this overall coefficient out in front also. So what this means is that these 3 theta functions form a triplet under the modular group. It acts on them as a triplet. And we can compute the average theta functions for this triplet by simply transforming the average that we know, which is theta 0, 0. And we find these answers. There are again some congruence conditions in the sum. So that computes this triplet of Eisenstein series. And finally, theta 1, 1 is a singlet under the modular group. Namely, it transforms theta 1, 1 to itself. And also, it vanishes at all the cusps. That's easy to check. So its average is actually 0. So the singlet Eisenstein series vanishes. Okay, so that's the boundary theory. And now we're interested in the bulk Chern-Simons theory. So I'll first review the construction of spin Chern-Simons theory. In the ordinary Chern-Simons case, the action can be written in terms of a bounding 4-manifold. So here the action is an integral over a 3-manifold M, which is the boundary of a 4-manifold M. And integrating by parts, we can write it as an integral over N. However, we have to check that this function doesn't depend on the choice of the 4-manifold M. So if we have 2 different choices of 4-manifold N and N prime, then the difference of the action between them is equal to the integral over a closed four-manifold of this function. But it's known that this integral is an integer. And so what this means is that the change in the action is equal to 2 pi I n. And so e to the minus delta s, which is the weight of the path integral, is equal to 1. And so this is a well-defined theory. So what happens if Q is odd? So let's suppose that Q is odd, but now we only look at manifolds n that have spin structures compatible with M. So in this case, it turns out that this integral is still an integer, even though Q is odd. So what this means is that we can define a spin Chern-Simons theory for odd Q, which now depends on the choice of the spin structure. Okay, so the average partition functions in this case can now be expressed in terms of partition functions of spin Chern-Simons theory on lens spaces. So now we have spin structures on the two tori, on the two solid tori, and we have a matrix transformation that acts between them. And again, we can consider the closed three-manifold that's formed by computing this inner product. And these two terms are the numerators in the Eisenstein series. So for instance, for the thermal ADS contribution, the transformation G is equal to 1. And so in this case, only the spin structures E01 and E00 are non-zero, and the other two vanish. So recall above, we had this congruence relation on C and D, that's C times D has to be even. And we can see how this condition arises from this formula. So for instance, if C and D are both odd, then up to the framing anomaly, we have that this transformation is equal to S times T times S mod 2. And by using the transformations of S and T on the spin structure, you can show that both of these matrix elements in the numerator actually vanish. And so what this means is that the summand of E00 vanishes. And so that leads to this congruence condition on C and D. In practice, if you want to actually check this formula, you need to use a generalized Gauss reciprocity formula in the presence of non-zero Wu class W. Okay, so now I want to speculate about a possible duality before averaging. So far I've given evidence for a duality after averaging. So we have a moduli space, we take the ensemble average, and then we get a Chern-Simons theory in the bulk. So in this Chern-Simons theory, there's no dependence on the moduli because, of course, they've already been averaged over. However, we can try to look for a more fine-grained holographic duality, and this would be a duality before averaging. So to do this, we include a Maxwell term in the Chern-Simons action. And so that's this first term here, dA wedge star dA. And there's some matrix, some coefficient matrix lambda that multiplies that. So E is dimensionful. So the effects of this matrix naively goes away in the infrared because the Chern-Simons term dominates. However, it turns out that the quantization conditions in the IR for the gauge field actually depend on this matrix lambda, shown by Gukov et al. And so even in the limit, even in the IR limit, lambda has an effect. And what you find is that for appropriate boundary conditions on the field, the partition function indeed matches the boundary partition function, but now with the moduli dependence. So this is a kind of holographic duality before the ensemble average. And in this formula, the moduli matrix lambda is related to the Hamiltonian in the theta function by these formulas. So here, O is the conjugation matrix, and this is the relation between Q and H, QH and lambda. So what this suggests is that we have a more fine-grained duality between Maxwell-Chern-Simons theory and the boundary theory before averaging over moduli space. And then after averaging, we have some kind of coarse-grained description of this duality. So one curious feature of the duality before averaging is that we never have to sum over geometries. This partition function is simply equal to the boundary partition function. So this is this also shows up in a paper of Eberhardt, who considers the full string theory in the bulk and shows that the sum over geometries is unnecessary if you take into account string theory. So possibly this is a more general principle in these examples of holography with an ensemble average. Okay, so that was the main part of my talk, and now I'll conclude. So I've discussed a duality between free boson theories associated to integral lattices and Chern-Simons theory. So one question that came up would be to find the bulk dual of a CFT, but now defined by rational Q, not integral Q. So in this case, the spin is rational, and so we now have particles with fractional spin on the boundary, which are parafermions. So in this case, we can actually compute the Eisenstein series pretty easily. Suppose that n times q is an even quadratic form. Then we just apply the same trick that we did for spin CFTs, and we can again compute the ensemble average. So with trivial spin structure, the Eisenstein series is equal to E for n times q, evaluated at tau over m. So acting on these E00 should lead to a new representation of the modular group. However, the bulk interpretation is not so clear because now we would have Chern-Simons theory with a rational level matrix, and such theories are not known to be well defined in general. So it would be interesting to understand the bulk interpretation. Another question would be to study orbifolds in this context, as discussed in Ida Zadeh's talk. As she mentioned, the 4-point function of twist operators is expressed in terms of a sum over rational tangles. So they did this calculation for even self-dual Q, and we're currently trying to understand the effects of general Q in this context. So in this case, the Eisenstein series should contain invariants of rational tangles, which would be analogous to the lens space invariants that I considered in this talk. So that would be an interesting future direction to understand these orbifolds. Okay, so I'll stop there for questions. Thank you for having me.
Let's thank Matt for the very nice talk. Any questions or comments?
I have a quick comment. So I think so. So you considered the sum over BTZ black holes, and over there, I think it's very lucky that the all the BTZ black holes are parameterized by this quotient group PSL2Z mod out gamma infinity. And that the same set actually, I mean, you need to sum over the same set to get the Eisenstein series. How will this work, for example, if you consider slightly general black holes which are not BTZ? So for example, even with two torus boundaries and something in the middle, how would you make a sum over all such geometries?
Yeah, so you could also ask about hydrogenous, or also, as you mentioned, two torus boundaries.
Yeah.
So those were considered in a paper by Maloney and Witten, and there's a sum over now Lagrangian sublattices now is the appropriate sum over geometry. So I don't have anything more to say about those, but that would be the appropriate sum in that case.
Okay, that would work because this would bring it down to the same discrete thing, because you have a sublattice and you have the symplectic group acting on it. So it's that would be SP2GZ over here. SP2Z is SL2Z. So
yeah.
But that is cheating though, because those are not all the kind of that's a very particular subset of such geometries. So
yeah, I agree with you. Yeah. So they showed that in that case they have to consider only that subclass, and so that's a kind of rule for the bulk theory, but it's not clear at all why that's the correct rule.
I see. And maybe just so it's a question for myself. So you get these, so you mentioned these quadratic Gauss sums.
Yeah.
They are, so Gauss sums are in general associated with Dirichlet characters. Is there a quadratic Dirichlet character somewhere? So you were associating a Gauss sum with gamma HCD, CD with coprime, I think something.
Yeah, let me go back to the definition. Yeah, I think that there is, but one second. Yeah, here we go. Yeah, so I think, so it's this definition here. I think you can write it in terms of the Legendre symbol equivalently. Yeah.
So you could write it as a Legendre symbol if one of them was a prime. So Legendre symbol, you need one of the things to be prime. And then I think this is since it's co-prime, it's maybe it's either a Jacobi symbol or a Kronecker symbol. I think it's Kronecker.
I see.
Anyways, that's just a detail. That was for myself. So thank you so much. I will see. This is very strange. I will see you guys in 8 hours after I sleep and wake up. Thank you so much. Bye-bye. Oh.
Any other questions? Questions, comments? No? Okay, if there are no more questions, let's thank Matthew once again. So, next talk will be at around 5:30 p.m. Japan Standard Time. It will be by Anne Tormina.
Yeah, I think we should mention that it's in about 4.5 hours.
Yeah, in about 4.5 hours.
Yeah. I can leave the discussion room open in case someone wants to discuss. Otherwise, I end the discussion for everyone. Okay, so.
Thank you, Matthew.
Yeah, thanks a lot. It's great talk. Yeah. Okay, so I'm going to end the meeting for all. So see you in 4.5 hours. Wait, 4.5 hours, right? Yeah, 4.5 hours.
Yeah, 4.5.
Okay, see you.